All right, so let me just remind you where we were. So last time we were doing, or I was anyway describing some computations in this quantum field theory X, compactified on a Riemann surface, which I take to be very small, and a circle, which I don't take to be very small. But I study the theory at low energies compared to the scale of this circle. Let me just say, I mean, what we get here, so there was this comment that somehow everything that we compute in quantum field theory is BPS. And I partially agree with this and I partially don't. I mean, for example, here we're calculating a thing which definitely depends on the radius of this circle in a non-trivial way. It's true that we compute it by kind of BPS kind of techniques, but at the end you get this thing which is not, well, I don't know what to say. It's not independent of the radius of that circle, that's for sure. So what was it that we were computing? So we had, we were studying M, the Hitchin integrable system, which was the moduli space, well, the Coulomb branch of this theory, which is fibered over B, the Hitchin base, which was the Coulomb branch of just the theory of class S, xg of C0. And we were studying some functions. We were studying some distinguished functions, which I think I was calling f, L, P, R of zeta from M to C. So where did these functions come from? So first of all, P was some path on the Riemann surface. P was some path on the Riemann surface like this. And then, so we were trying to get a number out of it. The way we were getting a number was to take a loop here, and then we have 4 dimensions left over, one of which is a circle. So this is R3 cross S1. And so we were taking a surface defect of the original 6-dimensional theory, wrapping it on here so it becomes a line defect in the 4-dimensional theory, and then wrapping that line defect around this circle. So then we get something that we can actually take the expectation value of, and that's what this was the expectation value of, let's say, the line defect, which we called LPR. It depended on a parameter R. Sorry, this is not the radius of the circle. I'll try to make it a script R. This was the representation of the group that we choose, depended on a parameter zeta, which kept track of the supersymmetries, or equivalently the complex structures on this hyperkähler space M, wrapped around the expectation value of this line defect wrapped around the circle. Okay, so that was the function that we were studying, and I told you last time that the deal was that if you look at what this line defect looks like in the infrared, you're led to a decomposition of this function of the following shape. So remember, U was a point of the Hitchin base. Sorry, I'll try to remind you of all my notation. So U is a point of the Hitchin base. Gamma is the electromagnetic charge lattice, which in this case is the first homology of the spectral curve. So this thing was a sum over homology classes of some integers that kind of depended on everything around. So I'll write all their dependence times some functions, some interesting functions, which I just call x gamma of zeta. So these functions x gamma of zeta are also functions on M. So the idea is you're taking this somehow complicated function that comes from the UV and expanding it in terms of simpler functions that come from the IR, which have to do with the abelian theory. And I told you the properties that these functions were supposed to have. First property was that x gamma of zeta asymptotically, if I take the parameter zeta and I go very near to 0 or infinity, it becomes something simpler. It becomes this function, exponential of a simple function, but one with an essential singularity. So here's z gamma. Okay, so another notation that we had before. Z gamma were the periods of the spectral curve. spectral curve is embedded in the cotangent bundle, so we have its periods. And theta gamma were the torus coordinates. So these are the coordinates on the torus fiber of the Hitchin invertible system. OK, so that was one property. And then the other property was that I better write the other property over here. So property 1 and property 2 is to be continued over here. Property 2 was that they had these jumps. So at the locus L mu, what was the locus L mu? L mu was the locus of u and zeta in the Hitchin base, the Coulomb branch, times c star, such that the period, so the period is a function of u, and if it just happens to have phase zeta, then we say we're on this locus L mu. So that's a real codimension 1 condition. So these are some kind of walls in this joint space. And at these walls, these functions were supposed to jump. And that jumping, so the jumping was given by a formula like this. It's a product of 1 minus x and mu to the power n, power omega of n mu, to the intersection pairing of mu and gamma. OK. So that's the formula I wrote last time. I didn't completely explain this factor, and I won't completely explain this factor, except to say that you can derive it from, I told you that there's this kind of breakdown of the infrared description of the line defect. That what's responsible for this jumping is the breakdown of the infrared picture of the line defect. And the way that the infrared picture of the line defect breaks down is that the line defect becomes very big. It's sort of very weakly binding some particle, and that particle is running off to infinity. So just from this picture of what's going on, you can calculate explicitly this factor. I mean, this factor is like a contribution to the Hilbert space that's coming from this particle that went to infinity. So it's some simple concrete thing. It's essentially, this is a picture essentially due to Denef. And that's sort of the key physical ingredient that derives this formula. So that's what I said, but I described this as if it was some kind of useful thing. And so far, it doesn't sound useful. So let me just say, what's the use of this? Well, I said that these properties determine these functions, and that's true. That's true essentially by kind of Liouville theorem. So if you have a function and you know its asymptotics at 0 and infinity, and you know it's, well, first of all, if it was holomorphic, then of course it would be determined by that, because the ratio of any two such functions with that property would be 1. Well, sorry, I said that badly. The ratio of two functions with this property would be a holomorphic function which is bounded everywhere, because it's holomorphic away from 0 and infinity, but it goes to this. So Liouville's theorem would just say that it has to be a constant equal to 1. And it's a similar thing here. This function is not holomorphic. It has these jumps, but the jumps are completely determined. So by some analog of Liouville's theorem, you can still prove that the thing is uniquely determined by this. But more than that, you can actually calculate the thing. So you can calculate this thing when the parameter r is large enough. So roughly when r times the minimum value of z gamma, for which omega of gamma is not 0, is big enough, much bigger than 1. I mean, you can put some actual effective bound there, but big enough. You can actually find these functions. And the way you find them is, so you need you solve a certain integral equation, which I'll just write. So this equation is engineered exactly so that its solutions will have these funny properties. So exponential of, so x gamma, it says that x gamma equals the sort of naive thing that comes from the pure infrared theory times some quantum, well, something which in retrospect you interpret as being kind of quantum corrections. So it's the sum over mu, pairing between gamma and mu, omega of mu. So this is coming somehow from this omega of mu I told you is the dimension of a Hilbert space of particles. And so it's, roughly speaking, what's happening is that these extra particles are running in loops and giving you a correction. Here's the form of the correction. But as I say, no one has yet done this calculation sort of directly. Instead, it's been done indirectly by observing that the functions have to have these properties. And here's if you have a function which solves this integral equation, then it has those properties. Yeah?
So given this expression, could I back solve, now that I know this, could I back solve this and say, oh, this is the Feynman diagram expansion for this one,
Yeah, maybe, right, so if you're really clever, you can now look at this and interpret it in terms of some conventional Feynman diagram computation. But I think there's some work involved. That's certainly not where it came from. Where it came from is what I just told you. This equation is actually really interesting. This equation, it looks exactly like an equation which is well known in physics called the thermodynamic beta ansatz for a two-dimensional system. That's basically exactly what this equation looks like. But no one has, as far as I know, no one has explained that either. So it looks very natural to explain this in terms of some two-dimensional system. A two-dimensional system of particles, but a slightly funny one. No, I guess that's right. This probably isn't in perturbation because it has to do with, yeah, these are all exponentially suppressed. These are kind of, yeah, no, I don't know the computation. I don't know exactly the computation which would produce this answer, except for the sort of indirect route that I told you. That's very typical in these kind of highly supersymmetric theories. You often get the answer by some crazy indirect way. It's also how Seiberg and Witten solved the original n=2 theory. They did it by, by very indirect kind of arguments, kind of global consistency arguments. It's a lot like what we do here. Yeah.
So you said it's the TBA for some spin system or XTJ?
Well, no, it's the TBA. I mean, what you can read out from this. See, that's the thing. I'm not telling you what system it is, but what you can read out from this is like what the number of particles is and what their scattering phase is. Yeah. So it looks bizarre because this parameter zeta, which is the twistor parameter, somehow is becoming the rapidity for that spin system. So that's weird because, yeah, yeah. This is supposed to be exact. This is supposed to be absolutely exact. OK.
What's R?
R is the radius of the circle on which we've. Sorry, which R? Where's R?
You said when
R.
R is large enough.
Yeah, that's right. So R was the radius of the circle on which we compactified to go from 4 to 3 dimensions.
So exact must mean plus corrections that are really, really fastly decaying in R? Is that like?
No. So this is completely exact.
You're saying that's exact because like when R is large enough that I'm like outside of some walls. I don't understand why it can both be exact and there's no R dependence.
Oh no, the problem is the following. The problem is that you may or may not be able to actually solve this equation. So I mean this equation. So this is an integral equation. This is not a formula, right? X appears on both sides of this formula. If you are able to solve this equation, then the solution has all the properties that we want to have. And if the parameter R is large enough, then you can show that this integral operator is actually like a contraction operator, so there's no problem with having a solution. But for small value of R, it's not obvious. It works much better than you can prove that it works. But anyway, I can't prove that it works for small values of R.
Where does R enter?
R enters into the equation here. So this x gamma semi-flat was exponential of R z gamma over zeta plus I theta gamma plus R z bar gamma times zeta. And the point is, roughly speaking, the way that you solve this thing is kind of by iteration. So you imagine that it was this x gamma semi-flat, plug that in here. You'll see that this integral is exponentially suppressed. This ray is exactly the ray on which this integral will be exponentially suppressed by this factor R z gamma. And so that makes the leading corrections very small.
Rewriting this, and then the place you've rewritten it in a way that makes it clear it's a contraction nothing for large R's.
Well, I mean, this, as it's written here, is not an integral equation at all. This is just some property that the functions are supposed to have. But that's right. So, I mean, the point is that a function obeying this property, if you look at how it behaves on either side of this ray L mu, it has a discontinuity exactly given by the residue. That residue calculation reproduces this. Yeah, this is some standard trick for producing functions. I think it's called the Plano's formula or something. Some standard trick for producing functions that have a given discontinuity. Okay, so this is some sort of effective procedure, and then So imagine that you've solved this equation, which you can really do. You can actually do it on a computer. And then the hyperkähler structure is given by, well, completely determined by the holomorphic symplectic form. Well, it's always determined by the holomorphic symplectic form. But the point is that the holomorphic symplectic form, as a function of zeta, these x coordinates are just are Darboux coordinates for the holomorphic symplectic structure. So I write it symbolically like this, concretely, dxi over xi, dxj over xj times epsilon ij. If you chose a basis for the lattice. OK. So that's the sense in which using this infrared structure has really bought us something. It's bought us the possibility of really finding this hyperkähler structure. OK, fine. Maybe just one remark. So this might seem funny. So these x coordinates are not continuous. They jump. And on the other hand, I'm saying that the holomorphic symplectic form is given in terms of these coordinates. So the point is that although they jump, this jump is a symplectomorphism. So the holomorphic symplectic form stays invariant.
So maybe I should take back my comment and say we could do the whole hyperkähler structure.
That's right. It's not exactly part of any single Rosansky-Witten theory. So on the other hand, it's controlled by the family of all Rosansky-Witten theories. So in that sense, yeah, I mean, it's somehow, maybe that's a qualitative point here, is that somehow, if you have a topological field theory depending on a parameter, it seems that it's important to study the whole family, not just a single one. That's essentially what we're doing here.
An x or a chi
Which one?
in the expression for the holomorphic.
These are all those, yeah, these are all x's.
Those are x's.
These are all x's. I didn't write any. I have like it's script x when we do it in LaTeX, math cal x. You call that, I mean, I call, these are all the same x. All these x's are the same x. They're all x on. Fine. So great. So I want to say more about what these things actually are and get to the role of surface operators in this story. Try to connect with the other talks today. So right. Yeah. First, let me just say one or two more words about the general structure here. So if I look at say fixed value of zeta, what are these functions? So these functions x gamma of zeta. So they're functions on. So they're functions on this hyperkähler space in a particular complex structure, which, so as we just said, are piecewise holomorphic. And so the picture, if I want to draw a picture of them, so they're piecewise holomorphic on M, but the locus on which they jump was determined by a condition that only involved the coordinate of the base. So the walls, in other words, are pulled back from the base of Hitchin's integrable system. So let me just draw the picture on the base of Hitchin's integrable system. So it may look something like this. Here's a sort of typical picture of it. So as we talked in the discussion session last time, you always have some of these discontinuity walls emerging from the singular locus, the bad fibers of the Hitchin system. And then when they hit each other, so each one of these walls is carrying some coordinate transformation like this. But typically, these coordinate transformations don't commute with each other. And so the requirement that these x gammas exist and that they're single valued, that they really exist as honest objects, implies that when these two things cross each other, something else has to happen. And what happens is that some new walls are born. So the typical structure of this picture is something like this, where at each intersection between walls, you have more walls coming out. And this sort of algebraic process you have to solve to find these other walls is exactly what Kontsevich-Soibelman uses, essentially the Kontsevich-Soibelman wall crossing formula. So in this context, that formula arises as just the global consistency of these functions. And so you get some complicated thing. Maybe here the walls are actually dense. So in some regions, the picture will be nice. And in some regions, the walls may be dense. So in the sort of nice cases, so all this came from having choosing the data that determined this whole picture was just the data of a Riemann surface, perhaps with some punctures. And at each puncture, I get to choose a residue, which was well, I said a nilpotent orbit. You can also deform the nilpotent orbits to take just semi-simple orbits. And in fact, if we take a C with punctures, like this, with semi-simple orbits attached, then this picture turns out to be quite nice. So there are kind of open and wall-free domains. In the Coulomb branch. So on the base of Hitchin's integrable system, there are going to be some nice open domains like what you see here. Or here. And in those domains, so in those domains we have a little breathing room, and in those domains you can ask, okay, so you've got these functions. What are these functions? And in those domains, these functions x gamma, what they turn out to be are the so-called cluster coordinates. So studied by Fock and Goncharov. So Fock and Goncharov studied on moduli spaces of flat connections. They studied some particularly nice coordinate systems, what they call the cluster coordinates. It's the cluster x coordinates. And so in sort of the good part of our story, we encounter these cluster coordinates. In the bad part of our story, so in the regions where the walls accumulate or where the walls are dense, you're meeting something that looks, from our point of view, equally natural. You're meeting some other functions which are just not cluster functions. So this is some kind of generalization of the cluster story. So these other functions look like they should be somehow equally good to study. So for example, so in the case where your Lie algebra was A1 and C is just a Riemann surface with no punctures, then we expect to recover. So what are we saying? So for every point of the Hitchin integrable system, we're supposed to get some coordinate system. So here that just means for a choice of a quadratic differential, a holomorphic quadratic differential, we're supposed to get a coordinate system. And in fact, there were such coordinate systems introduced by Bonahon. So just as an example of the kind of thing that you expect to get Bonahon's coordinates in this case. More generally,
The reason that there's the same number of such systems, or
they're parametrized by the same data, but it's even more than that. If you look at his construction of the actual coordinates, it's very, very close to the construction I'm about to tell you of how you get these x coordinates. His coordinates are just on Teichmuller space, I think. Aaron Phineas is working on this. Are you here? Aaron's not here. Yeah, their coordinates, I think they're just coordinates on Teichmuller space, which is like some slice of the moduli of SL2C connections. No, they're not Fock-Goncharov coordinates. I mean, Fock-Goncharov coordinates are only for punctured surfaces. So this is an unpunctured surface. So this is some generalization of Fock and Goncharov's thing. So the point is both of those somehow fit. Both of those arise automatically from this version of the story.
so do you know it to be false that there are no wall-free regions in the unpunctured case?
Yeah, I think it's false because I mean the walls. So the walls in this business are coming from the appearance of saddle connections, and I'm pretty sure that. Yeah, I'm pretty sure that it's false. Yeah.
Regions where the walls are dense, what happens to that wonderful contraction mapping expression you gave? Is it just that R has to get really, really big?
Yeah, R has to be.
Just sort of keeps getting bigger and bigger?
I mean, yeah, I mean, right. One thing is that the R cutoff might be pretty big in those regions. But the other thing is, I'm not saying that there's any problem with constructing the coordinates. I'm not saying that the coordinates don't exist.
But it's just that as I move, like I do this contraction mapping and it
Yeah.
just jumps everywhere.
Yeah, I mean, that's right. I mean, when you move a little bit,
I guess that's
yeah, I mean, the coordinates as I defined them, right? The solution of that contraction mapping problem is supposed to be a thing that has a lot of discontinuities. And so here it just has a lot of discontinuities. That's fine. OK. I didn't mean to spend so long on that. So yeah, so I want to connect this to the kind of physics that was going on here this morning. In David's and Kevin's talks. So let me tell you sort of another point of view on these coordinates x gamma. So suppose you want to know, for example, how did I know that they were the Fock-Gontreff coordinates? So I told you that, but how is that derived? So let me give you another description of these coordinates. So given a pair u and zeta, so in other words, a point of the Hitchin base together with a phase, I'm going to define a new kind of geometric gadget we call a spectral network called W of u and zeta on the Riemann surface C. So what is this network? So I'll just describe it to you kind of by the picture. So it's going to begin. So now this is a picture not on the Hitchin base anymore, but on the Riemann surface. It's going to look a little bit similar to the pictures on the Hitchin base. Namely, we're going to have some distinguished points. What are these distinguished points? These are the branch points. These are the branch points of the spectral curve. Right, so for every point of the Hitchin base, we have a corresponding spectral curve. And so we have some collection of branch points of that covering. So what are the branch points of the spectral curve? The branch points of the spectral curve are the places where two of the eigenvalues of the Higgs field collide. In other words, two roots of the, remember what the spectral curve is. Sigma u is given by the equation lambda to the k plus some r equals 2 to k, lambda to the r phi k minus r. Sorry, I got that backwards. Lambda to the k minus r phi r equals 0. So there's the spectral curve, and the branch points are exactly the points where this equation, where two of the roots of this equation collide. So say this branch point could be where root lambda I and lambda j collide, and from each branch point, in defining this network, we're going to emit 3 trajectories. Each branch point will emit 3 trajectories. Like this, like this, like this. What are these trajectories? So the trajectories are characterized by the equation. So here I had a branch point where two of my eigenvalues collided, lambda I and lambda j. And the branch point will be the place where the integral. So around this point, I could look at the integral of lambda I minus lambda j. That's some local coordinate around that point. And I ask, well, sorry, local coordinate in a simply connected neighborhood away from that point. And I ask for that coordinate to be real, or more exactly, real when I divide it by zeta. So this is a thing that depends on my choice of zeta. As I change zeta, this picture will kind of rotate into place. So each one of these branch points is labeled by a pair I and j. In fact, if I ask this to be positive, it's even an ordered pair. So here's ij, ji, here's ij. When I go around this point, I and j are being exchanged. So there's, say, a branch cut here, a branch cut here, a branch cut here. Let's say this is, so here as we flow a long way away, these trajectories may cross each other. So say this is jk, kj, kj, and so on, jl, lj, lj, and so on. OK, so we're drawing some picture on the Riemann surface, where from every branch point we emit 3 of these trajectories. And then there's an additional rule, kind of much like the splitting rule that we saw for the pictures on the Hitchin base, which is that whenever 2 trajectories cross, if I have a trajectory ij and a trajectory jk, they cross and make a trajectory, then we'll emit from the crossing point a trajectory of type ik. So when these cross, I guess jk and jl, so nothing happens. These cross. And then you just evolve them forever, and they go wherever they go.
IJ and KJ cross.
Nothing happens. The rule is that they have to ij and jk make ik, otherwise nothing happens. It corresponds to the roots of GL, the roots of GLN, the root alpha ij and the root alpha jk. Their sum is a root, which is the root alpha ik. OK, so here's the definition of this network. which I'm calling W of U and zeta. Here's a picture of it. And now, how do I interpret these coordinates in terms of this network? So the interpretation is like this.
So does this new on K line, it also obeys this equation?
Yeah, absolutely. So through any point whatsoever, right, I could just define a trajectory of this equation. So yeah, I mean, in other words, locally there's just a foliation of the surface by curves obeying this equation, and I just happen to include in the definition of the network, I include the trajectory beginning at that point.
The rule is against some statement about if you go all the way around and these things.
Right. So that's.
The wild elements that get trivial.
Oh, you're asking how did.
Which wasn't true if I go all the way. I mean, it's not true there, but things that are not under branch points.
Right. Like this one.
Yeah.
Yeah. So that's right. So one way of interpreting this rule is that some product of 5 matrices is the identity. Yeah, we'll see that in due time.
The angles of these rays at each at this point where they're born, where new ray is born.
Yeah.
Are the angles determined?
No, they're not fixed. They can be anything. They can hit each other with any angle. Okay, so
Actually, I think maybe this question was how do you decide the angles of the new ray?
no, the new ray is a trajectory of this first order differential equation.
Oh, I see, sorry.
So it's completely fixed. Okay, so to define these functions, these coordinate functions, x gamma of zeta on the moduli flat connections, what do we do? So we're given a point of the Hitchin moduli space, which we think of as being an SLK connection, nabla of zeta. So given a point of a Hitchin moduli space, we have this construction that gives us a whole family of SLK connections, say nabla of zeta. So given the SLK connections, nabla of zeta, we seek GL1 connections. So these are connections over the Riemann surface C. And in order to construct the coordinates, we're going to look for corresponding GL1 connections, which I'll call nabla ab of zeta, over the spectral curve, this k-fold cover. So the picture is like this. We're going to relate, we're going to relate a GLK connection, an SLK connection here, to a GL1 connection here, this k-sheeted cover. So what would you naively think? The thing you might first naively think to do is, if I have a GL1 connection here, I could make an SLK connection, well, a GLK connection at least, on this space just by pushing forward, right? Just take the direct sum. So take here, all the fibers here, just take the direct sum of those guys here. That'll have an obvious connection that just comes from taking the connection. So if I want to take a parallel transport along, say, this path, I would just take the direct sum of the parallel transports along the images of this path. That almost works, but it doesn't exactly work. The reason why it doesn't exactly work is that this is a branched cover. And so when we go around a branch point, a connection defined like that would have monodromy. So you have to somehow fix up that monodromy. So the way to fix it, so we're going to seek a GL1 connection on the cover with the following additional data. We're going to look for an isomorphism. Let's say iota. So we're going to look for an isomorphism between our connection downstairs and the push forward of the connection upstairs. But not everywhere. We're going to look for an isomorphism only away from these walls. So our connection will be literally the push forward. In other words, we're going to diagonalize, said otherwise, we're going to diagonalize our connection everywhere except from these walls. And then we're going to ask that this isomorphism should jump so at the walls, it jumps by an endomorphism of a particular shape. So an endomorphism of the push forward connection. So when I run into one of these walls, say of type ij, my isomorphism jumps by something of the form. It's just the identity matrix except for one non-zero entry in the ij position. So in other words, in short, we're representing this connection in local gauges which are diagonal, and then there's a gauge transformation when you go from one patch to another. But that gauge transformation is just this very constrained thing. It's just a unipotent matrix with one entry off the diagonal. So now here's the story. So in good cases, hopefully all cases, this condition is enough to determine this abelian connection upstairs uniquely. Determines it uniquely, or uniquely up to isomorphism, given Nabla zeta. So in other words, given this connection here, there's exactly one way of rewriting it in terms of a GL1 connection on the cover. So that's the kind of abelianization of flat connections. And then we define these coordinate functions, x gamma of zeta, which I first defined in a different way. We can think of them as being the holonomies of this abelian connection. So we had one function attached to every loop on the spectral curve. And now we're interpreting those functions as the holonomies of some GL1 connection. That's the picture. OK. And then the jumps. So now you can understand why these functions x gamma of zeta had this complicated jumping behavior. So this jumping behavior occur exactly when the network that I drew, when w of u and zeta jumps. So I gave you an algorithm for drawing some network. If you vary the parameters a little bit, the topology of this network won't change. But if you vary the parameters a lot, the topology may suddenly jump. And at the moments when the topology of that picture jumps, those are the moments when these coordinates jump. And they jump by the kind of formula that I wrote before. OK, so what does this have? Now I want to explain what does any of this have to do with physics? And second of all, why are the pictures so similar? So the picture that I drew, the pictures that I drew on the curve C and the pictures that I drew on the Hitchin base, why are they the same kind of pictures?
What's hiding in the hopefully all cases?
It's just that right now there simply isn't a general proof of this. So it's been done in a lot of examples, but it hasn't been done in general.
The statement which you don't have a proof of is the fact that
so it's the statement that given a connection, there exists this abelian connection, and conversely that there exists only one. Yeah.
do you have a procedure for producing this kind of abelian?
No, that's exactly what I do. No, there's no procedure for producing it, except there's a big class of examples for which there's a procedure, and we believe that it should work in general. But
is the SL connection flat?
Yeah. Sorry, both of these are flat connections. So flat connection here, right? I mean, we're looking for what are we trying to do? We're studying the Hitchin moduli space, which is the moduli space of given a point in the Hitchin moduli space, you get this family of flat connections. We're trying to construct coordinates on the space of flat connections. So yeah, and we're relating them to flat connections over this covering.
When you start with a connection on C and you're
Yeah.
looking for connection on sigma,
Yeah.
is the U, are you also looking for the parameter U, or
No,
you fix sigma and you fix U and you're looking just for this abelian connection?
yeah, you fix the parameter u. You fix the parameter u. Once you've got the parameter u, you have this network. And then the question is to find a connection which to find a connection with this property. Now that property, right, depends on which network you happen to be using. So u enters, but only enters in that way.
Is it clear that you can solve it for U and you can solve it for nearby U?
As long as those two w's are not separated by too crazy a set of walls. No, that's right. That's part of how you do it. So we proved that you can do it for some particular networks. And then you can get to any other network which is connected to those just by a finite set of walls. But no, it's not a general story right now.
Presumably everything's out the window when I'm like at these bad devices in the Hitchin base, and when I'm at like the sort of like very reducible connections and everything.
That's right. Okay. So now I want to try to say the sort of physical interpretation of this story. So question one, if you like, is what is the physics of these pictures? And a closely related question, why are they similar to the ones we had on the Hitchin base? So these are pictures on the Riemann surface. Why are they similar to the ones we had on the Hitchin base? Okay, so to start answering that, let's first. So we had one network, W of u and zeta, for every u and b. And so one thing we could do, of course, is just combine all of them. So each of these was sitting in C. We had one for every point u and b. We could combine them to just a single picture. Let me just call it W of zeta, which is now lying in the product of the Hitchin base cross the curve. Okay, and this is still a collection of codimension 1 walls inside of this product. Okay, and how are we going to think about this? Well, so before, the key thing was that we were drawing a picture on the moduli space, of some quantum field theory.
Why is it still codimension 1?
I mean, it's defined still by a codimension. Each wall is defined by a codimension 1 condition. It's defined by the condition that something is real. So if you have a bunch of pictures,
They would just take the product of the walls and make the walls.
No, it's not a product. I mean, you just have a bunch of slices, right? You have a bunch of pictures. Each one has codimension 1. And now you're making you're taking a bunch of them, right? The union of those things is still going to be codimension 1 in the bigger space.
Oh, okay.
Yeah. Okay, so before, the key thing was that we were drawing a picture on the moduli space of a quantum field theory. And now what I want to say is that B cross C, well, more exactly the cover, B cross sigma, it's almost B cross C, actually is the moduli space of something. It is the moduli space of a certain quantum field theory. What is that quantum field theory? It's what, a coupled 2D, 4D system.
And what is B cross sigma?
B cross sigma. Oh, sorry, it's like the fiber. No, you're right. It's like the universal, yeah. You're right. It's better to say the family. How do I want to write it? Family sigma over B. Yeah, B cross C would have been nice, but you're right. When we take the cover, of course, it varies. So sigma over B. So B itself was the moduli space of just the 4D system. And now this combined thing is the moduli space of something else. It's the moduli space of a combined 2D, 4D system. How do we get it? So we're going to get it by taking the 4-dimensional theory. We take the 4-dimensional theory, xg. This was the moduli space of the theory, xg of C naught. And we're going to put a surface defect in there. What is the surface defect? Well, remember, one of the ways that we could get surface defects.
So the not means that I took C and it was.
Yeah, that's right. So we have a point Z of our surface. And corresponding to that, there's a 2-dimensional surface defect, which I'll call S sub Z, which we can put inside of our 4-dimensional space, right? Because we had these 2-dimensional defects in the original theory. Now I'm just putting it at a point of the Riemann surface, and letting it spread out in the 4-dimensional space. So I'll get, in my 4-dimensional space, I now have some 2-dimensional thing sitting there. We'll call this surface defect S sub z. So then what can I do? So okay, why do I say that this thing has a moduli space? Well, one thing that's sort of evident is that I could move this point z around. So moving this point z around, I would be sweeping out moduli space, which would be just the curve. But now, if you look at the, so that's kind of a UV parameter. It's a parameter which is part of the definition of the defect. When you look at the thing in the infrared, what you find is that it has actually not just one vacuum, but it has a bunch of different vacua. And the vacua, so the vacua of the defect as z correspond to points zi and sigma, which are the pre-images of z. So that's how we get sigma. So you vary the defect z, and for each choice of for each fixed choice of the defect, you have the vacua which are lying on the cover. So altogether, once we include this surface defect, we have a theory whose moduli space isn't just B, but rather it's this universal spectral curve over B. So it's a 2-dimensional field theory, and that's right. So this SZ is like a little 2-dimensional field theory which is living inside the 4-dimensional thing. And so to choose a vacuum for that, we have to first choose a vacuum for the ambient thing, but then we also have to choose a vacuum for the defect itself. I'm saying that's what gives you this extra.
The choice of z is like this UV parameter you fix it again.
The choice of z is like a UV parameter. So if I like, we could have fixed z and just had the part of this thing over a fixed z.
So the moduli space is.
Yeah, I'm saying it in a kind of tricky way. So here, yeah, I'm including the UV parameter, which is moving the point z, as well as the IR parameter, which is just choosing a different, choosing one of the k different vacua. So if you want to hold z fixed, you should just look at the set of k pre-images of z.
Okay. But you don't get a sigma model to. Okay, so if you fix z.
No. We're not saying it's a sigma model into this space or anything like that. I mean, this is now a combined 2D, 4D system. I mean, that's right. The defect for any fixed value of z is just massive. It just has these k distinct vacua. That's all it has.
That's a generic thing, right? I've got k vacuums. Sometimes they.
That's right. Okay, yeah. So that's right. So let me try to say that. So indeed. So right. So statement 1 is that the infrared vacua of this defect as z just correspond to points which are the k pre-images of the point z. And so in particular, the infrared picture of the defect, or the infrared description of the defect. Well, what is the infrared description of the defect? So it's going to be a defect just in pure Yang-Mills theory. So it's a surface defect in the abelian Yang-Mills theory. Since we said all along, that if we sit at a generic point of the Coulomb branch, the infrared physics is just given by abelian Yang-Mills theory. And so this defect has to be some defect of abelian Yang-Mills theory. Well, what is it? So it's determined by the point zi of sigma just by the Abel-Jacobi map. Namely, so what does that mean? So given the point z, I get a corresponding point of the Jacobian of sigma, which is just h1 sigma with coefficients in u1. And so what is that? So given a particular vacuum of this surface defect, I want to describe what the thing looks like in the infrared. And what it looks like is a kind of solenoid. So think of a solenoid from electro. So it's this thing, yeah. So it's this thing that you study in when you study this U1 gauge theory is just electromagnetism, right? Classical electromagnetism. So you know this thing where you have like a coil of wire wrapped around, so it has a magnetic field inside of it. Outside of it, it doesn't have any electromagnetic fields at all, except that it creates a holonomy for the gauge fields. So there's a holonomy for the gauge fields around a solenoid. That's exactly what this surface defect is like. It creates a holonomy. For the gauge fields around the defect. So the infrared description of the defect, that's all that it looks like. It just looks like you've got a solenoid sitting in space. All it does is, it doesn't create any electromagnetic fields. All it creates is a little holonomy. It's a very trivial kind of thing. And what the holonomies are, how do you know what they're going to be? They're given by this Abel-Jacobi map. So here's a point of the torus corresponding to every point of the spectral curve. OK, so that's a very simple kind of tame description. Yeah, but now, so
Is your description just as good if I put multiple points?
yeah, you could put it. So that's right. There's a generalization of this where you have several different surface defects corresponding to different points of the Riemann surface, and you set them all on top of it.
Yeah, all on top of each other.
Yeah, just put all the defects sitting on top of each other. Yeah, I think in the infrared it would just look like you add up the.
Surface is on top of each
Oh, let's not do that. Let me not deal with that right now.
Is anyone going to, should I complain to the Abel-Jacobi map? You need to fix a point of sigma in order to find it?
Yeah, let me not worry about. Yeah, so you're right. You're right. There's some shifting of degree here, which let me not worry about. I mean, you're right. But now the story is going to be completely parallel to what we said in 4 dimensions, namely, so there's going to be some special points where the infrared description of the defect breaks down. And it breaks down exactly where one of the vacua, where, well, let's not say what goes wrong. It goes wrong. Okay, it goes wrong when there's a soliton connecting two vacua, which becomes extremely light. But the place where that happens concretely is it happens exactly at the branch points of this covering sigma C. In other words, so generically we just have k distinct vacua, and exactly at the branch points is where two vacua are kind of coming together. So there's some excitation that connects you from one vacuum to the other. That excitation is getting lighter and lighter. And at this point, you sort of can't have a low energy description that doesn't include that excitation. So anyway, so just as we had in the 4-dimensional story, we have an infrared description of the theory which is kind of generically good and occasionally breaks down at some special points. And now, so what are the walls? What are the parallel transports in this language? So we could study, not only just study the surface defect by itself, but we could study interfaces between surface defects. So it turns out it's possible to make, so the surface defect is BPS, and you can also make a BPS interface between surface defects. So here's the surface defect corresponding to the point Z1. Here's a surface defect corresponding to the point Z2. And here's some kind of interface between them, which I'll call L sub P. So you should think of these as the analog of the line defects that we studied before. This is like a line defect, but now it doesn't live just out in the bulk. It's a line defect which is constrained to live only on this surface defect, or rather only between these two surface defects. So the analogous thing in the picture of the Riemann surface, or the corresponding picture in the picture of the Riemann surface, these two surface defects corresponded to points, say Z1 and Z2. And now we're going to have a path that connects them. So the interface corresponds to a path. So before, line defects corresponded to closed loops. Now we have these interfaces which correspond to open paths. Yeah?
So are you suggesting that there's really... I'll take it back. It's a good question.
So just like before, all the interesting stuff came from studying line defects. Now, in this kind of refined setup, all the interesting stuff is going to come from studying these BPS interfaces. And just as before, they depend on a parameter. They depend on a parameter which is valued in C star, which keeps track of which supercharge is being preserved.
So I'm going to ask, but maybe this gets a stupid question.
OK.
So like you're saying I put these two-dimensional grains or whatever in the six-dimensional thing, and then I arrange them in this particular way. So that
Yeah, that's right. Just think of the brain. I mean, right. So each piece of this picture is kind of two-dimensional, right? Here it's a surface cross a point. Here it's a line cross a line. Yeah. So if you like, you could make a chain out of this thing, which would have no boundary.
somehow sufficiently upstairs, they all look the same. All of these.
That's right. They're all made. It's made from the same stuff, so to speak. It's made from the same six-dimensional defect. All of it's made from the same six-dimensional defect. We're just orienting it in a more complicated way. It's remarkable that it can be done supersymmetrically, but it turns out that can be done supersymmetrically.
For stay, I thought that there was like sort of maybe discrete parameters labeling the surface.
There were some parameters, and those parameters have wound up in this zeta. Oh, there was a discrete parameter labeling a representation. Yeah, that's right. Sorry. Thank you. So here we're studying the surface defect we're studying, since we're doing the AK theory, the surface defect we're studying is the one corresponding to the fundamental representation. Yeah, in fact, had we taken some other surface defect, we would have had a similar story, but instead of studying the spectral curve in the fundamental representation, it would have been the spectral curve in some other representation. So in fact, all the spectral curves have some kind of physical meaning here, corresponding to the corresponding defects. Yeah, that's absolutely true. Okay, so anyway, so I guess I can just say now why the pictures are the same pictures, or why the pictures are somehow related pictures. So it's the same question as we asked before in the bulk theory. The question we asked before in the bulk theory was, how do you describe the defect in the abelian gauge theory, in the infrared? And the corresponding picture here, so the infrared picture of the interface will represent it as a sum of interfaces in the abelian theory. But what does that mean geometrically? And let me just say what it means geometrically in terms of this Riemann surface. So we have this path here, and now that's going to get lifted up, just as we had before. That's going to get lifted up to some sum of paths. So there'll be one path like this, maybe another path like this, connecting various possible vacua that these defects could be at the two sides. So each interface here will get represented by some sum of possible interfaces of the abelian theory, between the defects of the abelian theory, which are just represented by points of the cover. Those are the vacua of the defect downstairs. And now, just as before, the sort of key thing that makes the story interesting is that this description, just like the other one, this description breaks down at some codimension 1 locus in the parameter space. So now the parameter space that we're talking about is B cross C. It turns out not to depend which sheet of the cover you're on here. So this description breaks down at some codimension 1 locus in B cross C, and that locus is exactly what I called before the spectral network. So that's the kind of unifying picture from which you can understand all of these different diagrams. And so somehow that's the most complete way, even if you're ultimately only interested in the closed loops, even if you're only interested in things in the four-dimensional theory, it turns out the good way to understand it is to think of them as just special cases of these open loops. So otherwise, if you want to study a topological field theory, or if you want to study a supersymmetric quantum field theory, it's better to study all of its possible kinds of defects. Not only the theory by itself, you should also include the line operators, you should also include the surface operators. You get a lot more structure when you do that, which is the same message that has been coming from David's and Kevin's talks today. OK, so thanks. I guess I'm done. Oh, I can give you the reference. It's it has the word Thurston symplectic form in the title.
Can you just say a little bit about what the 2D theory, the vacuum of that corresponds to the points, the spectral curve of the...
Yeah, I mean, some people would almost take that to be I think maybe maybe the best way for now, since the only interpretation that we had of the only interpretation that we've really physical interpretation that we've had of the spectral curve so far was in terms of this picture of the M5 brane. So it was a picture where you have an M5 brane here, and then you're kind of breaking it up into a thing like this. So if you just look for the supersymmetric configurations of the 5 brane, which near infinity asymptotically are sitting at this point z, it turns out that you can find them exactly things ending just on the preimages of z. Yeah, that's probably it. Yeah.
So if we consider the other surface operators, do you get some other kind of information, or is it?
No, that's a funny thing. So right. Using more surface operators, of course, their physics is also sort of independently interesting. But if you wanted to learn about the line defects of the original theory, it turns out that just using the at least for A, just using the fundamental representation is enough. It has to do with this. Well, never mind. So yeah, you don't get more about the 4D theory. Oddly enough. Yeah.
If you think of these surface operators, you see the dimensions, they get bigger and bigger.
Yes. Oh, yes. Well, sorry. Reduce them to 5 dimensions or to 3.
I was thinking 5, but maybe you can tell me anything else you can tell me.
Okay. Well, I can tell you about something about reducing them to 3. So. What's that? Well, let's start in 4, and then put the surface operator, the same surface operator that we've just been talking about. So yeah, so there is an interesting kind of connection. So I told you that the infrared description of the thing is given by the Abel-Jacobi map, right? So another way of saying that is that the infrared description of the infrared picture of what the defect looks like, for every point of the Hitchin base, I'm giving a point of the Jacobian. So what it looks like is like a multisection. And in fact, it turns out to be a complex Lagrangian multisection of this integrable system. So these electromagnetic phases that I told you. So the defect SZ corresponds to a complex Lagrangian multisection of M. And if I would compactify, the theory now on a, instead of compactifying it on a circle as I usually did in these talks, if I would compactify on a cigar and put this defect, yeah, what do I want to do? I guess I want to compactify on a cigar across a circle. So I'll get down to 2 dimensions. I'll put the defect at the tip of the cigar and then cross with just a circle. Now I'll get a boundary condition in that 2-dimensional theory. And that boundary condition will be exactly the boundary condition coming from this complex Lagrangian. There's actually 2 ways of thinking of it, depending on which way you compactify. So in one way of thinking of it, you get this. In the other way of thinking of it, you get the vector bundle dual to this, which is the vector bundle mirror to this. And that's the universal solution of Hitchin equations restricted to this point Z, which is a hyperholomorphic bundle. So yeah, so this is a BAA brane, and the mirror of it is a BBB brane.